we're not calling them prodrugs, but the others are forming through metabolic processes. So structural activity, relationship, and we are only looking, like if you have, as I had already mentioned, this is a general structure of our nitrosourea, whereby you have the nitroso group, you have the nitrogen, which can have an R. That R can be that glucose, which we have seen, and then you have the urea, and then you have another R. This R can be a methyl group, again, as in streptozotocin, or it can be the ethyl, the chloroethyl group, as in lomustine. So we are saying, number one, substitution with two chloroethyl groups resulted. We are just calling this not two group, but it's a two chloro. The chloro group is at position number 2, because you can have the chloro group at position, it's at position number 2. So substitution with the two chloroethyl group resulted in higher anti-cancer activity than either a substitution with a longer carbon chain or an unsaturated group. So we are only saying the reason why these drugs have this group here, this is what we are calling position 1, position 2, two chloroethyl group. Two chloroethyl group, because then you could put the chloro group here, you could substitute and the chloro group is here, but we are calling it a two chloroethyl group, gave us much higher activity than if you had put any other group. And if you had put another group which had a longer chain, all unsaturated, then you find that the two chloroethyl, the chloroethyl group was found to give us very good activity. The next part is substitution at both nitrogens now. One of the nitrogen is the nitroso nitrogen, and the other nitrogen, the urea nitrogen. Both nitrogen of the urea with two chloroethyl moieties. So with two chloroethyl moieties resulted in forced formation of camustin, which was found to be more active than the N1 methyl analog, for example, of mustin. So we are saying, again, the reason why we have camustin is because it was found, if you put those two groups, then the resultant molecule was highly active, highly lipid soluble, and indeed we did say that drug has very good ability to penetrate the BBB and can even be used for brain tumors. Then, among various 1,3-bis-2 haloethyl 1-nitrosoureas, iodo and bromo analogs could undergo decomposition in plasma, and bromo analogs are found to be active against certain cancer cells, whereas iodo analogs were found to be inactive. So we are saying they try to substitute, to put either bromo or iodine or chloro. It was found fluoro and chloro are the best. As we have said, the iodo and bromo are a little bit unstable. They could form, they could cleave, they could decompose. The compounds could decompose within the plasma, and iodo was even found to be not very active. So therefore, the fluoro and chloro are found to be the best. So that's what we're saying. Iodo and bromo analogs could undergo decomposition in plasma. Bromo analogs are found to be active against certain cancer cells, and iodo analogs were found to be inactive. So the best was indeed, however, chloro and fluoro analogs had the best activity. So, and that is why, again, of course, if chloro have good activity, there is no need of doing fluoro, because we know we do have a lot of chloro molecules in chlorine or chloro groups in our body, so there is no need of putting fluoro if chloro is giving us good activity. That's why we're saying most of these compounds are chloro derivatives, because chloro is found to be the best. The placement of chloro in the 3 position of relative urea nitrogen-neutral compounds with no anti-cancer activity. Now, the placement of chlorine in the 3 position. So, in other words, if you changed this, remember it was an ethylene moiety, you change it into a propyl group. So, replacement, and you change this into a propyl group, then the resultant compound was found not to be active. So in other words, we are saying ethylene moiety seemed to be the one with best activity. Again, if you replaced this with a methyl group or that with a methyl group, and also you replace this carbonyl group, in other words, you have thiourea. This is now thiourea. You have, instead of C double bond O, you have a C double bond S. That's thiourea. So you replace the urea with the thiourea, again, the compounds. And of course, with also replacement of that with methyl, those compounds were found not to be active. So in other words, we are therefore justifying the compounds we are calling camustin and lomustine, because the specific substituents that were found in those drugs were found to be the ones that were responsible for maximum activity. Detoxification or metabolism. Again, the detoxification can occur in two ways, either dechlorination or denitrization, the removal of the nitro group or the removal of the chloro group. So you can have the first method, whereby you have the lone pair of electrons. You can see that's the nitrogen, the same structure we have there. We have not changed. That's our nitroso group. So this lone pair of electrons can again move in there. If that moves in there, we will have a double bond there. And if that double bond is there, this nitrogen will have 4 bonds. So there is movement of this to that oxygen, and then it attacks that carbon there. So that means when that happens, there is cyclization, and that chlorine definitely will move. So there is cyclization to form this, which you can see is an oxo-diazo moiety. So it's a tetrahedron. Suppose it is an oxo. Can this see this an oxygen oxo-diazo moiety? So you form that, but that is not the end. Remember this hydrogen which was there. This hydrogen can comes in there. If it comes in there again, you will form a double bond there. You will form a double bond there. If you form a double bond there, that means that this carbon here will have 5 bonds. So there is a cleavage there and movement of the electrons to that, this movement of the electrons there. And if those electrons move there, that means that nitrogen is stabilized. So that is how you get the cyclic ring on its own there. And we get the remember the isocyanate. This is the isocyanate moiety, as we found.
To see if you are what you say you are.
That is the isocyanate moiety. So that, of course, then it can react with water to give us several products. So that is that's one of the methods to dechlorination. And of course, as you can see, these are spontaneous decomposition, usually because of the fact that the resultant molecule is at high energy level, it's not stable, so it undergoes decomposition to give you the most stable molecule, which indeed finally is the oxodiazo moiety or derivative. Then you can also have a loss of the nitro group. So you can have loss of this group, and that's all that has happened there. That group there is lost. It's a minus NO2 plus. And that, of course, so that's all that has happened there, just loss of that group. So that can also happen. So that's what we are calling as the 2 main ways of detoxification of the nitro. Also plays a role in resistance. Of course, once the drug undergoes that detoxification or that metabolism, then it ceases to have activity, and that's the source of resistance of these drugs. 2 major routes of inactivation have been identified. The first of these involves dechlorination, which is facilitated by cytochrome P450 and involves cyclization to give the 4,5-dihydro 1,2,3-oxadiazo and the isocyanate. Isocyanate also does the carbamylation of the proteins, as we had said earlier, in RNA. The oxadiazo can be further degraded through hydrolysis to several inactive products. The second route involves denitrization, which is in the case of camustin, has been shown to be catalyzed again by cytochrome P450 enzymes and glutathione S reductase. So we are saying so this is what we have already looked at that, and we have of course looked at that also. But we are seeing some of, so that's a different group now. So I think we are almost getting finished with this one. So we are saying we are saying some of the steps. Some of the steps are catalyzed by the cytochrome P450 enzyme, but I believe some of the other steps are also spontaneous rearrangement of the molecule. So again, that finishes the nitrosoureas. We have looked at the SAR. We have looked at the activation. I think we're done with the nitrosoureas. The next group, as I said, all these drugs we are looking at are all alkylating agents, but we are classifying them as per their structure. So it is their structure that is putting them in their different categories, but ultimately all of them are alkylating agents. Then the other class is the triazines. Sometimes you see this with an E, they are triazines. Again, we have dicarbazine, we have procarbazine, and temozolomide. But when I look at the structure of procarbazine, it is more of a diazine than a triazine. But I still found it to belong to this class. So we have the dicarbazine, procarbazine, and temozolomide. Again, because of their structure, like you look at the dicarbazine, we are calling it a triazine because of this free nitrogens. Again, if you look at this, we are calling it a triazine because of those three nitrogens. But this, I thought this, in fact, even when you look at its mode of action, it goes through a hydrazone. So it's really not a true triazine, but it's still found to be put in this category. So the triazines, where you have procarbazine, dicarbazine, and temozolomide, and dicarbazine and procarbazine, again, are prodrugs which generate methyldiazonium as the alkylating agent. Is activated. So again, it's better to look at the method of activation. So again, look, it is an inactive moiety, that is the structure of dicarbazine, and it's being activated through metabolic process. And once it's activated through metabolic process, let's see what happens. What has happened to this? So there is an oxidation. Which part is that? NH2 and CH3. And difference between those two molecules. Is there a change in position of double bonds? Yes, sorry. So it's cytochrome P450, but it's an oxidative end dealkylation. So it's an oxidative end dealkylation, catalyzed by cytochrome P450. So we are losing one of that methyl group through oxidative end dealkylation. So that is one. So that's why we are saying it's an oxidative end dealkylation to give us that. And that's all that happens, the first step. And then when that happens, it allows for the movement of electrons. I want to believe, when it is like this, it's too crowded. There's too much steric hydrons, and therefore it is not possible for even the electrons to move. So once that happens, this compound is in equilibrium with this other compound. If you look at this compound, this and this are actually constitutional isomers, constitutional isomers. That's the only difference, because in this one, the double bond is at this position here, and in this one, the double bond is at that position. Then nothing else changes really. So they are constitutional isomers. So there's just a shift, this lone pair of, so there's a shift from this to that, and that's why we are saying they are in equilibrium position of constitutional isomers, and this is the one now which allows for the movement of electrons. So these electrons can move in here, right? If they move in here again, this will be from three bonds, a triple bond. If that does happen, then there will be one electron coming here to stabilize that group, this nitrogen, and one electron coming this way to give here as an NH2. So of course, coming in of a hydrogen. So one electron goes to give us an amino group there, and one electron stabilizes that nitrogen. So again, we do have that group here, and this group. So you have that group there, we get our 5-amino imidazole 4-carboxylamide is that compound there, plus this. Yeah, there wamekosea hapa. That's why I was wondering. It should be a CH3. Hapa tumeandika Cl. So this is unfortunate. Correct it. That should be a CH3. Otherwise, you cannot alkylate. So this is supposed to be N triple bond N positive CH3 here, and of course that cleaves again, giving us the nitrogen, the dinitrogen, and our nitrogen and our carbocation CH2, and that our carbocation, sorry, CH3, because it is an external, methyl group, so it will be CH3 positive, and that CH3 positive is the one which is going to alkylate the DNA. Of course, this compound is stable and it's left like that. So that can happen that way for the carbazine. And then you also have temozolomide also. Temozolomide can react with water. Again, that's the structure of temozolomide. Let's see where the difference is. And then you have and there's a cleavage. You can see this is a bicyclic ring. That here is a bicyclic ring. On reaction with water, there is amide cleavage. So there's this amide cleavage here. Yeah, there's amide cleavage here. And of course, that ends as NCOH. So NCOH is this group cleavage here. And then the other group, this will go on its own. And it's a CH3, NH, CH3, NH. Because once you cleave here, this must become an NH, N double bond, N, and it changes the name. So first, the reaction is actually a hydrolysis of the temozolomide, hydrolysis of the amide, which is within the bicyclic ring of temozolomide, and with that hydrolysis, again, you get, of course, that carboxylic group. And then this compound, which is formed on hydrolysis, can lose carbon dioxide. So it can lose this carbon dioxide here to generate our 3 MTIC. Remember, MTIC is just the methyl triazinyl imidazole carboxylamide. So it can, this compound loses the carbon dioxide, goes here, and the process is the same. So the only difference is the structure and the fact that temozolomide starts with hydrolysis. And once it undergoes hydrolysis, it gives the carboxylic acid derivative, amide hydrolysis, carboxylic acid derivative, loss of carbon dioxide to give us the MTIC, and the MTIC will follow the same mechanism as the activation of the carbazine. So that is. Once we see that, then we can be able now to understand, because you can't be able to understand that. Generate amidodiazonium ion as the alkylating agent. The dacarbazine is activated by N-demethylation in the liver, a reaction catalyzed by cytochrome P450. Remember, it's an oxidative N-dealkylation. That is the starting point for the activation of dacarbazine. The formaldehyde is then lost to form a product which spontaneously degrades to form the 5-amino imidazole and the imidazonium. That one is, of course, we had already mentioned that. I hope you can. We had already mentioned that this compound here and the important group, the methyldiazonium ion. So it gives us that compound that is already a stable compound, and the methyldiazonium ion. And of course, the methyldiazonium ion is the one that generates the carbocation, and the methyl carbocation is the one who does the alkylation. The action of the methyldiazonium ion with RNA or DNA results in the methylation mainly at 7th position of guanine. The DNA fragmentation can also occur. We have already done that, because sometimes it's good to look at the structures before you can understand the explanation. That's the same. The only difference there is this one is showing us that once you form that, the methylation, here we have our methylation now.
There we have our methylation. And you can see that once the methylation occurs, that nitrogen at position 7 now carries a positive charge. Once it carries a positive charge, it means it will interfere. The way it will bond now to the adjacent molecules will be different. So you can see that you can have that nitrogen being protonated. And remember, we did say when you alkylate this group, we said there will be change in acidative basicity properties. There will also be depurination. We did mention that the things that can happen once you alkylate that group. Then, of course, the methylation can occur also on the oxygen at position number 6, and that's where you get the methoxy group. So again, remember, this is an oxygen which can bond through hydrogen bonding. Remember we talked about hydrogen bonding. You have now blocked it. Once you block it, then definitely you will interfere with the structure. With that, because that group there can no longer bind the other portions of the molecule through the hydrogen bonds. Remember we did mention the bases usually interact with each other through hydrogen bonds. So once you methylate, then that means you interfere with the bonds that help to place or help to put the bases in position, and therefore that will interfere with replication. Then you have procarbazine. Again, procarbazine, we have said it's also prodrug. Again, it is activated by cytochrome P450 or monoamine oxidases. So it can be activated by the cytochrome P450 or monoamine oxidases and to form the azoprocarbazine. So this is our procarbazine to give us the azoprocarbazine. And when the azoprocarbazine is just that this nitrogen and that nitrogen, there is a double bond here. So that's the azoprocarbazine, whereby you have a double bond. Here you had a hydrogen is a procarbazine, NH, and through oxidation is also loss of hydrogen. So through the loss of hydrogen, there is oxidation, and you form the azoprocarbazine. And then you have a further oxidation, and that further oxidation brings about oxidative hydroxylation of this methyl group here. So that methyl group undergoes oxidative hydroxylation. There we have the oxidative hydroxylation there. And then when that happens, then you have decomposition. And the decomposition occurs at this position. Decomposition occurs there. The decomposition occurring there. And once, or in fact, you can even almost call it's almost like an oxidative dealkylation, but I think I would prefer perhaps call it a decomposition. And when it happens there, when it cleaves, there is a cleavage rather. We can call it a cleavage. There is a cleavage there, and the compound, the whole of this compound now, the compound on this side now, that becomes an aldehyde. And that's an aldehyde there. This becomes an aldehyde. It is there, and then it gives us the methyl diazine. So you can see CH3 N double bond N double bond N. So methyl diazine, and this can either cleave to give us the free radicals. Remember, the free radicals can also be used in alkylation, or it can also change to give us the diazomethane, or what we are calling the methyldiazinone, methyldiazinone ion, and then the methyldiazinone ion, as we had said earlier, it will cleave to give us the methylene carbocation and the N2, and all those can cause alkylation. So we are saying the methyldiazine can do two things. It can either spontaneously give us these are free radicals, and of course these free radicals is what we are talking about, and that free radical can cause alkylation, or it can also rearrange to give us the diazomethane, and that diazomethane, or we're even calling it the methyldiazinone, or that methyldiazinone can again break to give us the nitrogen plus, of course, the carbocation, as we have said. So both the radical, the carbocation, both of them will cause alkylation. So that is through the method of cytochrome P450, and that of course is a method that will happen in the body, or in case there is, of course, there can also be oxygen within the tissues. So there can be also formation of azoprocarbazine, and this azoprocarbazine is the same as that azoprocarbazine, and that azoprocarbazine there can be shifting of the bonds. So you can see here the only difference here, the double bond, kindly note the double bond here is here. This is where we have our double bond, and that's the azoprocarbazine, just like this other compound here. All that has happened here is that one hydrogen here has moved in here with the loss of that hydrogen. So there is loss of one hydrogen and that bond moves here. So to get your double bond there. So now your double bond is here. So it's a shift. Usually a spontaneous rearrangement. Normally we call it spontaneous rearrangement. It usually occurs to be able to give us a very stable. Remember, even when we are looking at the metabolism of drugs like the penicillins in acidic media, we did look at those spontaneous rearrangements. So this is just a spontaneous rearrangement whereby you can see they're in equilibrium to try and establish the more stable molecule. So, and once this happens, this is now the hydrazone. So this was the azoprocarbazine. It's just a shift. It's not something difficult to understand. A shift of electrons, a shift of bonds to give you, of course, this is just the constitutional, positional constitutional isomer, which is the hydrazone. And now the hydrazone reacts with water to give us the methyl, again, hydrazine. That's a methyl hydrazine. So it reacts with water, and you can see it again cleaves this point, CH3, NH2. So it cleaves there to give us the methyl hydrazine. Once it gives us the methyl hydrazine, again, the methyl hydrazine can react with oxygen. Again, now the process is the same. So once it reacts with that, in fact, even the product here is also the same as we got earlier there. So it gives us the methyl hydrazine plus the same product there. And the methyl hydrazine is the one which undergoes oxidation or reaction with water, with oxygen, again, to give us the same compound. So there is quite some commonality in the process, a lot of commonality, but you can see that this drug is also a prodrug. It has to undergo metabolic activation for it to give us the active compound. Temozolomide also acts as a prodrug and is hydrolyzed in the body to form the MTIC, which decomposes like the carbazine to form the methyl diazonium. Carbon 6, again, the same, almost very, very similar as we had said, through hydrolysis. It requires to be deactivated through hydrolysis. So the molecule itself is not active, must be cleaved through hydrolysis. So with this addition of water, as we had said, cause cleavage of the bicyclic molecule to give us that molecule we had discussed, to give us the methyl diazonium ion. The methyl diazonium ion loses the nitrogen, and definitely it becomes the alkylating agent. That again is the triazines, where we have the procarbazine, dacarbazine, and temozolide. And we are saying again, they have a structure which allows them, to generate the active moiety. And the active moiety is for these ones, for the nitrogen mass that we saw, it was aziridinium ion. For this ones, the active moiety, just like the nitrosoureas, are actually the carbocations. You generate a carbocation, and that carbocation, being electron deficient, being an electrophile, allows is very readily reacts with the nucleophile, or readily alkylates the nucleophile because of the fact that it is highly electron deficient. Those we have talked about. The other one, again, also an alkylating agent, but again, because of its structure, it belongs to a different group, is what we call the alkylsulfonates. And when you see the word sulfonate, it means there is a kind of a there's a sulfur group. There is this sulfate group. There will be a sulfate group there. So we have the methyl sulfonate on this side and the methyl sulfonate on that side. So we are calling them butane 1,4-dimethane sulfonate. It utilizes two sulfonate functionalities as living groups separated by a 4-carbon chain that reacts with DNA to primarily form intrastud cross-linking at 5' position for guanine at position 5' of guanine. S cross is cross-linked with 3'. So we have the adenine 3' position. These are positions at the sugars. Remember, so the position guanine at position 5', this definitely must be the nucleus. Remember, they are nucleotides because the 5' and 3' are usually on the sugars, they're not usually on the bases. So the 5', which is on the guanine, so that means the guanidine moiety or the GMP, and of course also the 3' on adenine. So that means so those positions are linked together. So the 4-carbon chain that reacts with DNA to primarily form intrastud cross-link at the 5 position of guanine, and that 5 position is linked to the 3' position of adenine. So because there are two of them, one of them will bind the guanine at position 5'. The other position will bind the adenine at position 3'. So these two are linked together. So those two moieties are linked together. So that's what we're talking about. But of course, it must be, this group must leave, and that group must leave, and that's what we're saying. They're living groups. When this group leaves and the other group leaves, it means that this position will be positive, and then it is alkylate. It alkylates the DNA. When that again leaves, this will be positive. It alkylates the other position of the DNA, and that is how it will bring about its activity. And I think we can be able to see. So here you have your bisulfan, and all we are saying this is this is for the alkylation of the other alkylation. I don't know whether it's, I didn't put that one. So I didn't put the other. This is now, they can also alkylate just like the others, but this is not this one, remember, because that other one is for alkylating for the sugar positions. So here, this one is just the alkylating. They can alkylate, as we said, also at position 7. So if you have your position 7, which has electrons, it's a strong nucleophile, it attacks that group, the sulfonate leaves, and of course, that sulfonate, this will bind here, and this will be free. And that's the same thing we have there. So that binds there, this is free. So again, this attacks there, that is free. So you can see this is interlinking of position 7. So that's why we are saying this cannot be the guanine adenine. This is interlinking. This is interlinking of the two bases. So this one is interlinking of the two bases, and we know this is position 7. So this is the method of where they can bring about alkylation of the DNA at those positions. So the same bisulfan there, the same is just a short form, and there can be the alkylation of the nucleic acid at both positions. Of course, this is the metabolism. It undergoes glutathione conjugation. So bisulfan undergoes glutathione conjugation. When it undergoes glutathione conjugation, it loses. So the glutathione comes and it comes and it's remember, it comes and joins, it's usually GSH, comes and joins at the sulfur. It comes and joins at this position, and there is loss. Means that that's that position, and there is a loss of the whole of the other positions, and the cyclization. So it joins and they cyclize. So there's quite something which is happening here, because you find that it joins at the sulfur moiety. So the glutathione is glutathione SH. So it comes in as glutathione SH, and we lose the whole of that molecule here, and the cyclization. So SH, so we are losing the whole of this group. I believe this sulfur is the one from the glutathione, because remember it's glutathione, usually SH. So the SH comes in, and we lose the whole of that molecule, and also there is cyclization at the same time. So that happens, and of course you can see there's a loss of the whole of one of those molecules, and then once you have that, then stabilization, that is just loss, cleavage there, stabilization of that to give us a tetrahydrothiophene, and then the tetrahydrothiophene can undergo oxidation to give us a tetrahydrothiophene 1 oxide, further oxidation to give us the sulfolane, and then further oxidation to give us a 3-hydroxysulfone, hydroxysulfone. So this is the degradation, metabolic degradation, whereas the upper one is actually the activation. Mention that one of or both of the methyls of sulfonate ester moieties can be displaced by the nucleophilic N7 of guanine, leading to monoalkylated and cross-linked DNA. That's what I was telling you. The one I've shown, I've not bothered to show the other one, where they can bind at position 5 of one and position 3 of the other one. What we have demonstrated there, they can bind at position 5 and position 3, and the position 5 and position 3, both either guanine, adenine, or guanine and guanine. But at the same time, they can bind at position number 7, which we have just illustrated. So we are saying they can act in 2 ways, whereby they can do their alkylation at the position 5', 3' of both guanine or guanine adenine, all whereby they can do alkylation at position 7, as we already explained. The extent of alkyl sulfonate mediated DNA interstrand cross-linking is proportional to the length of the alkyl chain between the sulfonate esters. Or we are saying this is the one we are calling the this one is the one we are calling interstrand cross-linking. So this is one strand, remember, coming down, one strand of DNA, one strand of DNA. So this is one guanine on one strand, and another guanine on another strand, and therefore the alkyl group, which has originated from the bisulfone or from the alkyl sulfonate, has come in between. And this is where we are saying the ability for intercalating. This is what we are calling interstrand alkylation. What we're calling interstrand alkylation is dependent on this length here. So the longer it is, the easier it will be able to do interstrand alkylating. That's all we are saying there. We are saying the extent of alkyl sulfonate mediated DNA interstrand cross-linking is proportional to the length of the alkyl chain between the sulfonate esters. Like what we have, the compound we are looking at, balsulfone, it's a tetramethylene group. It has four carbon atoms, and contains balsulfone shows less interstrand cross-linking capability than hexamethylene. This is 6 or octamethylene 10. We're only saying for interstrand, because the interstrand, these drugs requires kind of to intercalate, to be in between these 2 strands. So the longer the alkyl chain, the easier it is for that molecule to fit itself. The other one was intrastrand. The intrastrand is where we are talking about, where you have GA, 5' G, guanine, and 3' adenine, 5' and 3' guanine sequences. So the intrastrand cross-linking also occurs preferentially at those groups. But what we are saying mainly, what happens is the cross-linking, and of course the cross-linking, we are saying it is dependent on the length of the alkyl group. Alkylation of cysteine sulfhydryl groups is yet another mechanism of cytotoxicity. Remember, in the body, we do have many amino acids, many proteins, which have sulfhydryl groups and proteins, and therefore They can also undergo alkylation, just as we said earlier, the carbamylation of proteins. So there can also be alkylation of sulfhydryl groups of proteins, but that will be mainly responsible for toxicity. We have one more group only, I think. This one is very short. We can look at it very. Can we look at it very quickly, or you are tired? Can we look at it quickly, or what is your opinion? Can we look at it quickly? It's a simple one, so that we finish the alkylating agents. So then, oops, even my power is gone. So the last one is the organoplatinum complexes, where we have the drugs cisplatin, carboplatin, and oxaliplatin. Again, they are alkylating agents. It's only that they have a different type of structure, which puts them in a different category. So we have the platinum 2 is an electrophile that can significantly bind proteins. Inactivation of the platinum drugs is caused by the presence of diodes in albumin, glutathione, and other proteins. So you see what we are saying here. This is our cisplatin molecule. This, you can see this ammonia, that's ammonia. So these groups are ligands. These are ligands, and then you have the platinum and then the chloro groups. Again, you can see the same ligands, platinum. So very similar, but of course, the other groups that are attached are different. Here you have chloro group. Here the different group they are attached. And then oxaliplatin, of course, also sharing the same, because you can see this one will behave as a ligand because it's already NH2. It would have been an NH because of the two bonds, but you can see it's an NH2. So again, there is some structural similarity. Structure and mode of action. The structure consists of a central platinum atom covalently linked to two chlorosubstituents, two ammonia molecules that act as ligands. The overall structure is neutral and reactive. Once cisplatin enters cells, however, it enters an environment which has a low concentration of chloride ions. The chlorosubstituent of cisplatin are displaced by neutral water ligands to give the reactive positively charged species, which act as a methylating agent. The electrophile binds strongly through covalent bonds to DNA individuals containing adjacent guanine units. Covalent platinum DNA links within the same strand or intrastrand cross-linking are also formed. It's likely that this takes place at N7 and oxygen 6 position of this. Again, we had already mentioned. So let us look at it so that we understand. It doesn't look like, so this is the cisplatin in the plasma. So it moves through the lipid membrane and gets into the cytoplasm. And all we are saying, you look here, there's lower concentration of chloride ions. It reacts with water, and once it reacts with water, it loses its first chloride ions. So water just is replacing the chloride ion. So water is replacing the chloride ion. Remember, the chloride left with the electrons, so it replaces the chloride ion, and you have a water molecule there. And of course, the resultant molecule is positive because the chloride left with both electrons of the bond. Then again, another water molecule comes in, and you can see this is that H2 positive. Another water molecule comes in, and another chloride ion is replaced, and you have this charged moiety and the two chloride ions. Now it is this moiety that intercalates, and as it intercalates, it loses these two hydronium ions, and the platinum is the one who joins the DNA directly. So now when you have that is our activated moiety through replacement of the chloride with a hydronium ion. All we are saying, it comes, that ion, you can see this is the NH3, NH3. There is a platinum. It has lost. It's both hydronium ion and directly is attached. So you can see this here. This is guanine, and this one here is adenine. So it is actually cross-linking, interstrand cross-linking between one strand and the other strand, and it's just sitting in between there, and therefore holding the two strands very tightly, and it will not allow for replication. So you can see again the mode of action. There is similarity, of course, and some differences, but we are saying we must generate the active moiety, but this moiety is just generated very simply when it moves in reaction with water, replacement of chloride, and with replacement of chloride happens twice, and of course the moiety has the 2 positive charge, and that is what goes for the DNA. So that's what I wanted us first to see. So when now we read, we understand. Like nitrogen mustard, the platinum complexes are bifunctional and can accept electrons from 2 DNA nucleophiles. Intrastrand cross-link most frequently occurs between adjacent guanine residues, referred to as diguanosine dinucleotides. In other words, on one strand, you can have on one strand here. So this is one strand, sorry. You have one strand, you can have a guanine there, and you can have another guanide. You can have some other bases in between here. But all we are saying is that your cisplatin can come in between, and it will alkylate that, alkylate that, and also come there. So this is the adjacent guanine moieties, and because it is within one strand, that is why we are calling it intrastrand. Adjacent guanine residues referred as diguanosine dinucleotides, adjacent guanine and adenine residues. One can be an adenine and the other one can be a guanine, just like all the others. They can both be guanines, or one can be adenine and one guanine. As the one we have seen one was adenine, the other one was guanine, but they can also be both guanine. Interstrand cross-linking, which occurs much less frequently, usually involves guanine and adenine bases. Again, intrastrand, the only difference is that one of the bases is on one strand and the other base is on the other strand. So now the drug comes in between here. And because you can see this drug has a small shape, has a small size, it might not be able to activate this one and this one at the same time. That's why we are saying intrastrand cross-linking occurs much less frequently as compared to the intrastrand cross-linking. That we have looked at. That is also associated with significant nephrotoxicity and neurotoxicity that is dose limiting. Because we must understand that these drugs, unfortunately, because they can also alkylate, the normal cells, they will also cause quite a lot of toxicity. And of course, toxicity is very limiting. It's very limiting in the usage of the anti-cancers, because the toxicity can be extreme. You can have severe vomiting and severe diarrhea, weakness, and so on. So the toxicity, hepatotoxicity, of course, the hair falling off, and so on. So one of the major problems or disadvantages, of course, of cytotoxic, giving these cytotoxic drugs or giving these anti-cancer drugs is their cytotoxicity or their toxicity. Is their cytotoxicity, because, as we said, the normal cell and the abnormal cell have very little difference. In fact, as we have seen in most of the mechanism of actions we've seen, apart from where we were saying there is a tumor which could produce more of a certain enzyme than the normal cell, and therefore you go for selective toxicity when you go for both enzymes. More often than not, the cell and the normal cell and the abnormal cell are very alike, and therefore you will find that the drug will bind both on the normal cell and on the abnormal cell and cause you a lot of toxicity. Of course, it's only that, again, in the tumor, there is a lot of cell division. In the tumor, there's a lot of cell division. So the tumor will be requiring a lot of the nutrients, to be requiring a lot of the nucleotides, a lot of them. And therefore, it can be able to take in the drug. And as it is doing, because it requires to do a lot of cell division, a lot of growth, as it is building its DNA, then it can take in the drug because of the fact that there is a lot of activity within the abnormal cell. But otherwise, it is a very big challenge. And of course, there is a lot of toxicity with these drugs. After that, of course, with that, we've moved to the antimetabolites. We have done the antimetabolites. So now on the next lesson, God willing, we'll have is now to do, I think, the miscellaneous. The miscellaneous are about 3 or 4 drugs. Once we are done with them, then we'll close the anti-cancer drugs. Is there any question?